Okay, so second day for natural logarithmic function differentiation. So again, like I said, most of our derivatives using logarithms, you can choose, like this, some of the stuff we're going to do today, you can choose any base for the logarithm, but we want to use the natural logarithm just because it makes the derivatives a lot easier. So let's go through and look at this example. Now, we're going to do a couple examples using this logarithmic differentiation. Some of them you have to use it for, but some of them you just kind of have it as an option. So if we look at this here, y equals x raised to the sine x, this is not really something that we can do a derivative of using the exponent rule, where we would subtract 1 from the exponent and then or bring that out front and then subtract by 1, because your exponent has to be a integer, okay, or a number. It can't be a function. So we need to think of a way that we can bring this down out of the exponent. And the only option that we have of doing that is using logarithms. So I'm going to just rewrite this here. If we have y equals x raised to the sine x, we want to get this out of the exponent. So what we're going to do is we're going to take a logarithm of both sides. Now you can choose any base, but like I said, I want to use the base of e so that it's just a lot easier to do it. So we can do ln of x raised to the sine x. Okay, so excuse me. This is what we need to do to allow us to bring the exponent out front. Okay, so what we're left with now is ln of y equals sine x times ln of x. Okay, so we're going to have product rule on the right hand side, but you know, it's something that we can actually do, where the derivative of x raised to the sine x is not something we can do. So now we're going to take the derivative, because that's our goal, is to get to dy dx, or y prime is how I'm going to write it, because I want to try and simplify it. So the derivative of ln y is 1 over y, and then from implicit diff we have times y prime, or dy dx if you choose to write it that way. And then your right hand side, if we take the derivative of this, we have to use the product rule. So the derivative of the first is cosine x times the second is ln x plus the first, which is sine x, times the derivative of the second, which is 1 over x. And now we want to solve this for y prime. So y prime is equal to, I'm just going to multiply both sides by y, and then we have cosine x times ln x plus, and I'm just going to rewrite this a little differently to make it look a little simpler, sine x over x. Don't cancel out the x's, we can't do that. Now we want this to be all in terms of x. So my last step is to replace this y with something that will leave me with only terms of x. And we know that right from the beginning, that was equal to x sine x. Okay, that's written in the problem. Y was equal to x sine x. So I'm just going to replace that, and then that'll give me my final answer. So y prime, or dy dx, if you choose to write it like that, is x raised to the sine x times that stuff there in the parentheses which is that. So there's your final answer. Okay, final answer. Okay, so for problems like this, you really don't have any option other than using this process called logarithmic differentiation. But for some problems, like the next example we're going to do, you do have some options. Sometimes using the logarithms makes it a little bit easier. So let's first of all look at a couple of steps here. This is basically what we want to do. It's mainly used when you're raising a variable or a function raised to a function or something like that, where you're trying to get that exponent or that function out of the exponent. And again, I would highly suggest you take ln of both sides. You do have the option of log, but just remember, if you do a different logarithm, your derivatives are a little bit more difficult. And then we simplify, take the derivative, maybe simplify a little bit more. because we want to get that dy dx or y prime by itself. So looking at this example here, this is not one that we are required to use the logarithmic differentiation, but it is one that if we do logarithmic differentiation, we can actually simplify this a little bit. So let me show you what I mean. So I'm going to start off by taking ln of both sides. So ln of y is equal to ln of this whole right-hand side. So x minus 2 squared over the square root of x squared plus 1. Now, why did I do it that way and not just use quotient rule? Well, for two reasons. One, these not only have quotient rule but chain rule inside of them, so that kind of makes it a little bit easier, because now, like, instead of saying the chain rule with like your squared function and then your inside x minus 2, or on the denominator is a better one to look at, the outside function is square root and then the inside x squared plus 1, that derivative becomes more challenging to do. Where using logarithms, again, like in the last one, the exponent can come down to eliminate the need for a chain rule. But also, this being divided will split this up into the top minus the bottom. So just to simplify this a little bit more, we can do ln of the top, which is x minus 2 in parentheses squared, minus ln of the denominator, which is square root of x squared plus 1. Okay, now it becomes an easier derivative to do. So we're going to take the derivative now. So the derivative of ln y is 1 over y times y prime equals, I'm going to do two things in this step. I'm first of all going to bring this down out front. I'm not going to do it in two separate steps because that's a waste of time. So I have a 2 times the derivative of ln x minus 2 is just 1 over x minus 2. And then minus, this one, remember, we can write square root, we can write that as an exponent of 1/2. So I'm going to bring the 1/2 out front, times the derivative of this now is, remember, whatever's inside goes on the denominator, x squared plus 1, and then the derivative of that goes up top, so 2x. So hopefully you're following along with what's happening there, and if not, let me know. I can show you more steps. So let's take this, simplify these 2's. Other than that, there's not a whole lot we can do. I'm going to multiply both sides by y again, so y prime is equal to y times 2 over x minus 2. I don't want that parenthesis in there. Let me clean that up a little bit. It looks a little messy. X minus 2. There we go. That's better. And I also don't want that there. Let me take another step back. Minus x over x squared plus 1. You can combine these into one fraction if you want to. That's really just going to depend on how the answer looks. So what I'm going to do is I'm going to replace, first of all, y with what I know about y. I mean, it's equal to this mess right here, right? So y is equal to x minus 2, quantity squared, over the square root of x squared plus 1. Times, if I do this, let's say if I want to combine this into one fraction, we would have to multiply this one by x squared plus 1, multiply this by x minus 2, to give us that common denominator of x minus 2 times x squared plus 1. And then up top, we would have 2x squared minus x squared would give us x squared plus 2x plus 2, if I did that correctly. Okay? And then another thing that we can do here is, just to simplify this a little bit more, we can get rid of one of these x minus 2's because they would cancel out. Okay, and then these x squared plus 1, x squared plus 1, this would be to the 1/2, and this is 1, so that's going to be 3, or I'm sorry, x squared plus 1 raised to the 3/2. because we would have 1/2 plus 1, which would be 3/2. So our final answer, I would say completely simplified, would look like x minus 2, x squared plus 2x plus 2. And then all over, depending on how you would see this written, you might see it like this, x squared plus 1, that quantity cubed, underneath the square root, or you may just see it written as a 3/2. But that is completely simplified right there. Okay, so we did a lot of algebra in that one. So if you have any questions on the algebra, just let me know so I can explain it a little bit more. And one more that I want to talk about here is just finding the derivative of this. Now, why are there absolute value bars around the cosine x? This is where I'm not entirely sure how much you guys cover logarithms and exponentials, so it's just something I wanted to throw in. But if you remember logarithms, the parent function for logarithms, whatever it is, whether it's ln or a log of any base, doesn't matter what the base is, of x, your domain for this is strictly, let me get rid of that. It's strictly greater than 0. Okay? So we can't plug 0 into a logarithm, and then we also can't plug any negatives in. So that's why we have the absolute value there. Now, we would have to further define the domain of this, because the absolute values takes care of all of the negatives, but the absolute values do not take care of any of the zeros. So actually, we could also, in addition to the absolute value bars, we would also need to say that any increment of pi over 2, we're also going to have a problem, because cosine of pi over 2 is 0, and we cannot take ln of 0. Okay, so we kind of have this inherited domain from ln that kind of understands that we cannot have 0 or negatives in here. So really, all we need to do is just, when we take our derivative, we're going to say 1 over the absolute value of cosine x, and then times the derivative of the inside would be negative sine x. Okay, now, like I said, because we kind of have that idea of the inherited domain for cosine, we know that this is going to be positive. It can't be 0 because it's under the denominator of a fraction. So really, we can just look at this as 1 over cosine x. So what is negative sine over cosine? And hopefully you know that that is negative tangent. So negative tangent x would be our final answer for that one. There is this kind of like a formula for your absolute value, like if f of x is the absolute value of x, then when we do the derivative, and I don't think this is something you're expected to know, it's just something I kind of came across when I was looking at this. This is what it would be equal to if f of x is the absolute value. It would be x over absolute value of x times f prime of x. I actually just came across that not too long ago, and just kind of used what we know about derivatives to explain these types of problems before. And it still comes out to be the same thing. Even if you do it this way, you still get the same answer. So, multiple ways of doing the same problem. So here you go. Here's a couple of problems for you to try. I believe it's 9 or 10 problems in there for you to try. And again, just let me know if you have any questions on any of these.